Sketching a graph of a function with given conditions can be a little tricky. It's hard to kind of sort through what the conditions are really telling you about the function and then sketch a function that fits them. I think one of the reasons these can be so difficult is there's a lot of leeway still within the conditions that they're giving you. There's a lot of things that can be happening, not at the points that the conditions specifically tell you about, which can make it tricky to know if you're missing something or if you're doing it right. So in this video, I wanted to show you an example of what process I go through and what steps I go through when I'm trying to do one of these problems, where they give you conditions or properties that a function needs to satisfy, and you sort through those properties and piece together how that actually looks on a graph. If that's something that you have a little bit of a hard time with and would like to be better at, I think this is going to be the video for you. So be sure to stick around to the end, and let's go ahead and jump right into it, and I'll show you what I'm talking about. Sketch the graph of a function f that is continuous on the closed domain from 1 to 5 and has these given properties. There's going to be 4 properties that we have here. We need an absolute minimum at 1, an absolute maximum at 5, a local maximum at 2, and a local minimum at 4. So the first thing I'm going to do here is just kind of point out, or just highlight, I should say, where we want minimums and maximums. So first of all, we have an absolute minimum at x equals 1, and then we have a local minimum at x equals 4, okay? And then we'll go with this. So we have an absolute maximum at x equals 5 and a local maximum at x equals 2. Let's think about, again, kind of just the differences between a local versus an absolute maximum and minimum. So local means it's just higher or lower than all the other points really close to it. Absolute max or min means it's higher or lower than all the other points within the domain. So in this case, we are given a domain of 1 to 5. So we don't really know anything about exactly the height of this function. We don't have any information on y values of this function. So it's really kind of arbitrary where we want to put our y-axis in relation to our function. So I'm going to go ahead and basically just put the whole function above the x-axis, which again is just kind of an arbitrary decision. But the point here is we do know that we have a specific domain. Our entire function exists between 1 to 5. So between x equals 1 to x equals 5. So if we were to label our x-axis here, 1, 2, 3, 4, 5, we only need to look basically between x equals 1 to x equals 5 to sketch our function out. Now, what we know is that we have an absolute minimum at 1. So basically our function is as low as possible within this domain. So whenever I'm saying in this example as low as possible or as high as possible, I only care about this domain. We're only worried about this domain of 1 to 5. That's the only part we need to kind of worry about at this point. So our function is as low as possible at x equals 1. So basically, wherever we want to put this point of our function, let's just say we put it here. This is at x equals 1, y equals 1 maybe. It doesn't really matter what the y is, but the point is the rest of our function, all the way for the rest of this domain, needs to be above this point, because we know that we have an absolute minimum at x equals 1. So basically the rest of our function needs to be up above this kind of red dotted line here, based on the fact that our function is going to be going through this point. Okay. Similarly, if we want to look at our absolute maximum occurs at x equals 5. So basically at x equals 5, our function is going to be as high as possible. So the rest of our function within this domain from 1 to 5 has to be below this like greenish blue dotted line up here. So basically our entire function needs to exist between this like box, basically. It needs to go through this point here and this point here at these corners of the box. The other piece we need to make sure is that we have a local maximum at 2. So basically we need to have some sort of a curve like this, where we kind of are going up toward that point from the left and then going down to the right. So basically we have this little kind of local max, like an N shape, where the top of the N is at x equals 2. So basically at somewhere along this vertical dotted line here, we need a local maximum, but it needs to still be below this line up here. So it doesn't really matter where we put it. We just need it to be below that line and above that line. But what we are going to need to make sure to do is kind of come up from the left over here and then go down to the right over here. Okay. Then we are going to have a local minimum at 4. So similarly, we need to create a local minimum at x equals 4, which is going to be more of like a U shape, where we are kind of coming down from the left, hitting our local minimum at the very bottom of this U, and then going up to the right. So that's going to be at x equals 4. And again, it doesn't really matter where we put this point height-wise. We just need to make sure it's above this dotted line, this red dotted line down here, and below this greenish blue dotted line up here. Now, we also know that this is going to have a local minimum, so we probably also want it to be below this point so that we can kind of come down from over here, curve up somewhere down here. So like down here maybe, we need to come down from the left and then curve up as we go off to the right. So we kind of have this general flow of where our function needs to go, where we're having exact perfect little tops and bottoms at these local maximum and minimum points, and then, you know, kind of reaching a maximum at the right, top right corner, and reaching a minimum at the lower left corner here. So these are really the only 4 pieces of information we have, other than, I guess, the fact that we know we have a function that is continuous throughout this entire domain. So from 1 to 5, we need to have a continuous function. Essentially, we need to be able to draw this whole function from the left edge of this box to the right edge of this box without picking up our pen. So that's really pretty easy to do. We really just need to make a continuous line that connects all the dots that we've gotten here, creating local maximum and minimums where we need it, and then an absolute maximum and minimum where we need it as well. So we have our absolute minimum, our local maximum, our local minimum, and then our absolute maximum, exactly where, you know, we had these properties that told us where those were going to be. Okay. If you found this video helpful, I think you'll find my weekly live streams, which I typically do every Monday night at 5 o'clock Pacific time, helpful as well. Because this example that you just watched actually came from one of my weekly live stream videos. So if you did find it helpful, do me a favor, hit that subscribe button and bell icon down below so you'll be notified when I go live next week. And you can come join and get whatever calculus questions you have answered as we work through some problems and hopefully have a good time. Hope to see you there.